Yeah.
Okay, so good afternoon, everyone. My name is Prayush Kumar, and today I wanted to talk about the promising uh, results that machine learning and AI applications have already demonstrated or slash promised in the field of gravitational wave astronomy, and also to discuss where we can go from here in this field. So the field of gravitational astronomy is a new branch of astronomy where we, instead of observing electromagnetic radiation, we look for gravitational waves um, uh, arriving at Earth from all sorts of um, sources out there in the universe. At the moment, we have three instruments that are capable of detecting these waves. The two LIGO instruments in the US, instrument in Italy that I'm showing pictures of here. These are all interferometric detectors capable of detecting gravitational waves of extremely small amplitude. So our primary sources right now are inspiraling two-body systems of black holes and neutron stars, which are some of the most compact objects in the universe that inspiral under the radiation reaction of the gravitational waves they emit. And as the orbit loses energy, the two objects come closer and closer, ultimately to merge and form a single black hole that sheds away its asymmetries and forms a nice curved black hole sitting quietly at the end. And the entire wave train that this process emits is passes through Earth and through these interferometric detectors to be observed by us, right? So this is a relatively new field. Only in 2015 were we able to actually make the very first detections. It took about 4 decades of preparation, both in the instrument, on the instrument side as well as the software side, to actually be able to see these extremely weak signals. And since then, we have observed nearly 100 mergers of two black hole systems, which I'm showing here in this visualization, which shows the masses of the inspiraling binaries, as well as the mass of the post-merger black hole that these binaries form that have already been seen with LIGO. So all of these blue circles here, they represent the black holes that LIGO Virgo have already seen. And the orange circles at the bottom here represent the neutron stars in double neutron star systems that LIGO Virgo has seen. And they can be compared to the observations of neutron stars from the electromagnetic spectrum that that are shown the red dots and the yellow circles here. And so we can see that already LIGO Virgo has contributed in terms of being able to see the most number of black holes that any spectrum in astronomy. Okay, so so in this talk, essentially, I'm going to focus more on the machine learning AI applications to this field and not delve into the classical methods that we have been so far using, right? So here is a brief flowchart that describes the anatomy of this entire research field as it stands right now. So we have our compact binary sources out there in the universe that emit gravitational waves, which are observed by the detectors here on Earth. The data coming from these detectors is passed through a recalibration phase that converts the raw data into a strain time series data, which is supposed to contain noise plus a signal, gravitational wave signal time series, if the signal is present. Of course, if not, then it simply contains instrument noise, right? And so from here, the challenges begin. So the first challenge, of course, is to actually detect the presence of gravitational wave signals in this data time series that we get from our instruments, right? And that forms this task is performed by the gravitational wave detection engine, which is so far based on a match filtering algorithm and some other signal consistency tests that took a couple of decades to develop. And the output essentially from this entire complicated stage is something like this. It's a list of triggers or possible gravitational wave events with a single number called their signal to noise ratio or SNR that measures their probability of being an actual signal. So what we find is that most of the triggers coming out of this stage are actually purely noise triggers. They're purely artifacts of instrument noise interacting with this detection engine, right? And you can see from the numbers on the y-axis here that we have millions of noise triggers. Thankfully, the way we designed these engines is such that all these noise triggers, they cluster together at low values of the signal to noise ratio statistic, or maybe a log likelihood statistic, depending on which particular variant of this engine we are using. And actual gravitational wave signals, they stand out above the crowd. They stand out above this entire background if we are doing this detection stage correctly. And that is how we are able to say that, hey, there is a signal present in our data, and we can state a certain statistical confidence to which we know that this is a real event and not a noise artifact. Now, once we have seen the signal, this becomes the input to our second stage in this entire pipeline, which is a Bayesian parameter estimation framework, which takes this data and compares it against our general relativity-based waveform models, specifically millions of waveforms generated by these models, in order to reverse engineer the source properties for this signal, the properties of the actual binary, the astrophysical environment around that binary, etc., that led to the emission of this particular gravitational wave signal, are calculated within this Bayesian parameter estimation framework. Again, classically, right? And then these catalogs of source properties for all the gravitational wave events we see are used for further downstream science, such as estimation of the astrophysical formation scenarios in which such two-body systems form, the population statistics of these two-body systems, information about the expansion of a universe that they may carry with them, and other fun phenomena that we may want to measure from these signals. But in this talk, I'm not going to talk about this downstream science. I'm only going to talk about the upstream pieces that we need to make all of the downstream science possible in the first place, right? And that is where neural networks and AI have already been applied to show promising results, right? So that would be these stages here. So I'm going to talk about these two main big questions of this of the field of gravitational astronomy, and how ML and AI have already shown some promising results here. So let's talk about the detection problem first, right? So why is detection hard? Well, it's hard because the signal's space-time is incredibly stiff, and even black holes are only able to create fluctuations in the geometry of space-time at a very, very small amplitude, with a very, very small amplitude, right? So our typical signals are almost always dominated by instrument noise. And you can see this is a typical long duration signal shown in a red trace here, embedded within this noise that purely is of instrumental origin, right? If we convert this time series into a time frequency map, we are barely able to see the presence of the signal, at least with the help of our naked eyes, right? So this makes the detection of these signals difficult. And the other thing that makes their detection difficult is that oftentimes there are glitches in our instruments that can cause ringing in this time series, ringing-like features in the time series that is output from the detectors. And these noise-like features can often mimic gravitational wave signals. So not only are algorithms supposed to dig them out from noise, they're also supposed to discriminate them from non-Gaussian features of the noise to begin with. So between these two, that's why it took a couple of decades for the traditional methods to be perfected, or at least brought to the level of perfection that they are today, right? So neural networks and, well, machine learning, in fact, was first applied to the detection problem as early as 2016, when George and Huerta, two researchers at NCSA and UIUC, they took a toy problem where they took a substantially simple description of the signals that we expect, and they embedded them in instrument noise. And they showed that using a deep CNN, convolutional neural network, it is quite possible to actually uncover the signal's presence with a speed up of more than 10 to the power 3 when compared to the traditional match filtering search algorithms, right? Now, why is this speed up important? The speed up is important because we want to be alerted to the presence of signals as quickly as possible, because often these merger events, when the two objects actually collide with each other, the collision can sometimes produce electromagnetic radiation. So if we are able to know about these events very quickly, then we can pass along that information to our electromagnetic observer counterparts. And we can request them to point their telescopes out in the sky and look for electromagnetic radiation from these events. So that would be a complete multi-messenger observation of a single event in multiple spectra, right? So that's where the importance of the speed up comes in. And they also showed that the deep CNNs are actually better than some other algorithms in machine learning, which is what these two panels here depict. So a couple of years later, another incremental work showed that they can also attain a good level of sensitivity with traditional CNNs, including in the presence of higher harmonics of the gravitational wave signals, as you can see. So in the top three panels are the dominant mode gravitational wave emissions shown in orange, and the blue curves show what the signals look like in the presence of higher harmonics. And you can see that these higher harmonics can substantially change the frequency content, especially towards the end of these signals, right? And so this work was an incremental work, which showed that even this can be detected. Again, same year, another group in the UK, they applied CNNs to this detection problem again. And the key feature of this work was they did a more careful statistical analysis of the output of these neural network probabilities. And when they applied this to one of the events, GW150914, you can see the strain time series from the Hanford and Livingston detector in these two panels. And you can see the output of the CNN in terms of the detection probability as shown in green here. And near the time of the event, you can see that the network clearly detects the presence of an event, right? And so they also, as earlier papers show, that for high enough signal to noise ratio, say above values of 10 and higher, the detection efficiency of these networks can be quite high. Now, remember, none of these papers have yet talked about discriminating their detections from otherwise noise features. And that is one of the open questions in this field. So another paper last year that we put out does something different. Here, what we did was we took really long signals, which are characteristic of binary neutron star merger signals, and they can be easily up to half a minute or even longer in length, right? And if you look at the time frequency spectrogram, they are actually visible in this, right? So what this paper showed that it is possible to use CNNs to actually alert us about the presence of an incoming signal before the signal has completely arrived. So in these 6 panels here, the time of 0 here is the time at which the two neutron stars merge, or the black hole and a neutron star, they actually merge with each other. So this t equal to 0 corresponds to the end of the signal right here in this panel, right? And we can see that for a 5 solar mass black hole colliding with a 1.4 solar mass neutron star, or a 10 solar mass black hole colliding with the same neutron star, for such systems, the particular neural network that we chose can actually alert us up to 10 to 15 seconds in advance before the entire signal has actually been seen by the LIGO-Virgo detector, right? So this is moving more towards what we want ideally in terms of being able to send out alerts to our electromagnetic telescopic partners. right? So moving again to the second problem now, which is once we have detected the presence of these signals, can we reverse engineer the property of the sources of these signals? So again, the difficulty in measuring the source parameters are the same as before. The first is that the signal is much weaker than the instrument noise. Second is we also want ideally to be able to know these source parameters in low latency, which would mean within a few seconds to a couple of minutes of the arrival of the signal, right? And that is important because if we know that a particular event is originating from a neutron star, only then we will be alerting our electromagnetic partners, EM observation partners, and not when the event is coming from the collision of two black holes alone. So this would eventually lead to a lot of saving in terms of telescopic times. So, and finally, when compared to the current match filtering based Bayesian analyses, neural networks can hopefully, give source parameters faster, even if not in low latency. We can certainly hope for them to give us faster results than what we currently get, which can easily take between hours to a few days for each event, right? And this definitely becomes a problem when we enter into the next generation of our instruments, where we likely will see several events per week, right? So current methods are definitely not scalable to the future. So here to this problem, there have been a couple of papers, although all of them have been more...
Sorry, Prayush, is your talk much longer or?
It's a couple of more slides.
Okay.
Yeah. So all of these applications are rather preliminary in nature, and they either attack a toy version of the full problem, or well, actually, all of them attack only a toy version of the problem. So here is one paper from 2020 where they take a variational autoencoder and they try to measure the source parameters from a very simple non-spinning binary black hole system. And while they're able to measure the masses, for example, M1 and M2 are the masses here, the DL is the distance to the source, their results do not quite satisfy the statistical purity that we need from the probability distributions that they give us, as you can see from the PP plot not being a diagonal line here. Another paper in the same year using roughly the same neural network topology gives much better results. They can be compared to conventional MCMC results, as has been done in this picture, and they get much more controlled posteriors. But again, they attack the toy version of a problem. And finally, this last paper that I wanted to talk about, they use neural networks to learn the one-dimensional and two-dimensional posterior distributions directly. And for each parameter, they train an independent neural network. So this approach is promising, but it's actually prohibitively expensive in terms of training the networks to begin with. So to summarize, I want to point out that ML and AI have already been applied to the key problems in gravitational wave astronomy, but the current applications are mostly at the proof of concept stage. And the main problem, as we in the field understand, is that it's not yet clear how we interpret the results coming from these neural networks in terms of the statistical confidences that we can put in the gravitational wave detections that these AI algorithms will make, or the posterior probability distributions that these neural networks provide us with. Also, none of the current applications are quite scalable to a future detector network of 5 instruments, of which LIGO India will be a major member of, right? And sorry. So this is where we stand currently in terms of how ML and AI have already been applied. And clearly the results show a lot of promise, but in the future, a lot more maturity is required as to how nuanced is our application of AI algorithms to our problems. Currently, the application is more at a black box level, but I feel it'll take we will need to break down the problems into smaller bits and pieces and apply machine learning algorithms to smaller bits and pieces to come up with a unified and statistically purer framework for doing inferencing on our gravitational wave data. So that's it for me. Thank you so much for listening.
Thank you, Prayush.